Ever wish AI could learn complex reasoning without needing, all those expensive human labels or those really tricky domain-specific checks?
Yeah, exactly. Because traditional methods like reinforcement learning from human feedback, RLHF and RLVR, reinforcement learning with verifiable rewards, they're pretty powerful, sure, but they definitely hit some big hurdles.
They cost a lot, right?
Right.
And sometimes they can pick up unwanted biases, or they're just, limited. Only good for tasks where you happen to have perfect data just lying around.
And that's where this idea of reinforcement learning from internal feedback, RLIF, comes into the picture. It's basically a new way for these large language models to learn using signals they generate themselves internally.
Okay, so this deep dive is all about one specific method called INTUITOR. It's from a paper we're looking at today. And it uses the model's own self-certainty, like how confident it feels about its output as the only reward. No external stuff at all.
Right, and what's really striking, honestly, is that INTUITOR, using 0 correct answers, manages to match the performance on math problems compared to methods that actually need those golden answers.
Plus, it generalizes way better to totally different areas, like code generation. So our mission today, let's unpack how INTUITOR works, figure out what these pretty surprising results really mean, and talk about why this kind of intrinsic learning might be a huge step towards, more autonomous AI. Welcome back to the Deep Dive. Today, we are taking a really close look at the paper, Learning to Reason Without External Rewards.
Yep.
And our goal here is to really get our heads around this new approach, how LLMs can learn complex stuff without needing external labels or predefined answers based just on the paper itself.
Right. So the paper introduces this whole paradigm they're calling RLAF reinforcement learning from internal feedback, and then they propose INTUITOR as like a concrete way to actually do it.
Okay, so before we jump into the brand new stuff, maybe we should quickly recap why the methods we already have, like RLHF and RLVR, that the paper mentions, why they aren't always cutting it for what we need next.
Exactly, it sets the stage. The paper points out that RLHF, using human feedback to align models, it works, but it's expensive. You need all that human annotation time, and it can sort of inadvertently bake in biases from the people doing the ratings or even the reward model itself.
And then you've got RLVR. That's where you use automatic checks, right? Like running code through a test suite or checking a math answer.
Yeah, and that's great if you have those perfect, very specific verifiers. And critically, the paper stresses this, you need gold standard solutions. The right answer for math, the complete test cases for code.
Which isn't always feasible.
Not at all. It's costly to create that data, really hard for more open-ended creative tasks, and it limits how well the model can generalize. If you train it only on tasks with perfect checks, how does it handle something messier?
Okay, so that frames the challenge pretty clearly. How do we scale up AI training for complex, maybe even totally new tasks, especially when getting that definite external yes-no answer is difficult or maybe impossible? Thinking about future AI that needs to be more autonomous.
And that is precisely the gap RLIF is trying to fill. It's framed as a kind of paradigm shift. Let the LLMs learn from signals they generate themselves intrinsically.
The potential upside there seems pretty big. The researchers talk about, reducing the reliance on all that costly supervision.
Yeah, and using rewards that aren't tied down to one specific task format. Plus, enabling learning even when you just can't get external verification.
Imagine training models on, brand new scientific problems or tasks that are just inherently fuzzy without needing an army of labelers or a custom checker for every single thing. That's kind of the promise here, right?
The vision behind RLIF, yeah.
And the specific method they really dug into in this paper is INTUITOR.
Yes, INTUITOR. The core idea is surprisingly simple, but also quite elegant. Just use the model's own confidence as that built-in reward signal.
Confidence. Okay, that feels a little fuzzy. Why would optimizing for just feeling confident actually make the model better at reasoning?
It does seem a bit counterintuitive, doesn't it? But the hypothesis they put forward is that, when an LLM is uncertain, when its probabilities are spread out, it's probably struggling or maybe going down the wrong path. So they figured if you reward the outputs the model is more certain about, you should, in theory, steer it towards more coherent, logical, and hopefully correct ways of thinking.
And they pin down a specific metric for this, self-certainty.
Correct. Self-certainty. As they define it, it's the average KL divergence between the model's probability distribution for the next token and just a uniform distribution.
Okay, KL divergence. So higher score means more peaked, more confident distribution.
Exactly. They call it mode seeking. It likes sharp peaks. This is contrasted with something like entropy, which is more mode covering, meaning it might prefer broader distributions.
And they also mentioned it's less prone to getting tricked by just outputting longer stuff, unlike maybe perplexity sometimes.
Yeah.
And it actually gets better if you look at multiple possible outputs.
Yeah, those are good points they make. The idea is by pushing the model towards outputs it feels strongly about, you're encouraging things it internally believes are higher quality, more likely to be right.
So how did they actually implement this? They plugged it into an existing RL framework.
Right. They used GRPO, which stands for Group Relative Policy Optimization. They basically took the GRPO algorithm, but swapped out the usual external reward, like the math check, with their internal self-certainty score. Same underlying mechanics, just a different source for the reward signal.
Okay, quick refresher on GRPO for anyone maybe less familiar. The basic idea is you get the model to generate, say, a bunch of different answers or solutions for the same input. Then you score all those attempts based on some rule, and you update the model so it becomes more likely to produce the ones that scored higher.
Precisely. So with INTUITOR doing the scoring, you sample the outputs, you calculate the self-certainty for each one, and then you use those relative scores. How confident was it on output A versus output B to figure out which ones were better from the model's own perspective? Then update the policy to favor generating those high certainty outputs more often. They have a nice diagram, figure 2, that lays this out.
All right. Conceptually, that hangs together.
Yeah.
So the big question, how did this self-certainty thing actually perform when they put it to the test? They trained on the math data set, used Quinn models, various sizes, 1.5 billion up to 14 billion parameters, and tested on a whole suite of benchmarks. You mentioned GSM8K, Math 500, Live Code Bench for code.
Yeah, LCB, also CRU, XEVALO, MMLU Pro, and AlpaCaiVol for instruction following. A pretty broad set.
So what were the results? How did it do on the math problems it was trained on?
So this is pretty remarkable. On the in-domain tasks, Math and GSM8K, INTUITOR actually matched the performance of GRPO.
Okay, matched it. But wait, GRPO was using?
Exactly. Table 1 spells it out. GRPO, in this comparison, was using the gold answers, the actual correct solutions, to guide its learning. INTUITOR used nothing external, 0 golden answers, and it still performed just as well on those math benchmarks. They also had a variant, GRPO PV, using plurality voting, which also matched.
Wow, okay. Matching supervised results without any supervision on the core task that's already pretty significant. But you mentioned it really shone somewhere else.
Right, this is where it gets really interesting. Generalization. Specifically, moving from math training to completely different domains, like code generation. When trained only on math problems, INTUITOR showed way better generalization to Live Code Bench and CRU XEVAL compared to GRPO. GRPO trained on math didn't really seem to get much better at code.
Can you give us a feel for the numbers there? How much better?
Absolutely. Table 1 makes it quite clear. On Live Code Bench, INTUITOR saw a 65% relative improvement over the baseline model it started from, GRPO. Basically 0 improvement transferred from the math training.
65% versus 0. That's a huge difference.
Is. And on CRU XEVAL, it was a similar story. 76% relative gain for INTUITOR versus only 44% for GRPO. Still better than Grayline, but INTUITOR's gain was much larger.
There's that specific example they gave too, right? The small Quinn model on Codeforce's problems.
Oh yeah, that's a great illustration. The 1.5 billion parameter model. Before INTUITOR training, it scored 0% on those coding problems, just spat out repetitive garbage. After training with INTUITOR only on math problems, remember, it learned to generate coherent reasoning steps and structured code, and its accuracy jumped to almost 10%.
That's incredible generalization. It's not just getting better at math, it's somehow learning a more general reasoning capability that it can apply to code, and even fixing fundamental output problems.
Exactly, and it wasn't just code either. They found INTUITOR also significantly boosted performance on instruction following tasks, especially AlpaCaiVol. Again, it outperformed GRPO, and for the smaller models, it really cleaned up issues where they were just outputting gibberish before. You can see that in Table 1 and Figure 3 as well.
Okay, so beyond just the accuracy scores, do they notice any other, maybe more subtle, interesting behaviors emerging from this self-certainty training?
Yeah, a couple things stood out. One was about the learning speed. Table 2 shows that really early in the training, like just 10 steps in, INTUITOR was already showing better performance on the math tasks than GRPO.
Faster initial learning. Why might that be?
The researchers suggest it's because self-certainty is a more continuous and maybe process-aware signal. It gives feedback along the way. Whereas the GRPO reward for these math problems was just a binary correct or incorrect at the very end. So the internal signal might provide richer guidance earlier on.
Makes sense. And then there was this thing about fostering structured reasoning. That sounds really cool.
It is. This was maybe one of the most fascinating emergent findings. The paper notes that training with INTUITOR seemed to encourage the models to produce long-form reasoning. Like on benchmarks like CRU, XEVALO, and LiveCodeBen, the INTUITOR-trained models would often generate, paragraphs of natural language explanation, like step-by-step thinking before they actually output the final formatted answer, like the JSON or the code block.
Whoa, so it's not just spitting out the answer. It's like showing its work first, even though it wasn't explicitly told to.
Kind of. It's like the model is reasoning things out for itself, writing it down, and then providing the final output it feels confident about. This emergent pre-reasoning, as they call it, wasn't directly rewarded.
But the hypothesis is?
The hypothesis is that this process actually helps the model build confidence internally. By articulating the steps, it sort of convinces itself that its final answer path is sound, leading to higher self-certainty for that overall generation.
That's wild. So optimizing for confidence naturally leads to the model explaining its reasoning.
It seems that way in these experiments. Figure 6a and some appendix examples show this evolution beautifully on LiveCodeBen. First, the model outputs invalid code, then it learns to output valid code, and then it starts outputting valid code preceded by this natural language reasoning.
That's a really compelling side effect.
Yeah.
Okay, what about the robustness of this whole self-certainty idea? Could the model just learn to be confidently wrong or game the system somehow?
That's a crucial question, absolutely. They actually tested this directly. They compared using a fixed offline self-certainty score, basically, scoring based on how confident the original model was versus an online score that uses the model's current evolving confidence levels.
That's what happened.
Figure 7 shows it clearly. The offline scorer, it was vulnerable to what they called reward exploitation. The model figured out ways to trick the static scorer. Like, it learned to just add text from already solved problems into its output, because those look like high-confidence sequences to the old score. The score goes up, but the actual accuracy completely tanks.
Reward hacking. A classic problem. So it learns to fool its past self.
Exactly. But the online self-certainty, where the scorer adapts along with the policy, that prevented this kind of gaming. It led to stable, continuous improvement, which is obviously critical if you want to scale this approach.
Okay, so using the current model's confidence is key. Any other robustness checks?
Yeah, Figure 8 had another interesting finding. Policies trained with INTUITOR actually become better at using their own self-certainty signal to tell the difference between their correct and incorrect outputs later on. Even compared to models trained with external rewards like GRPO, the INTUITOR models showed a wider gap in self-certainty between their good and bad answers.
So they become better calibrated internally. And quickly, did they mention anything else from ablations, like that KL penalty?
Right, the KL penalty.
Yeah.
Table 3 showed it didn't make a huge difference for the main math task, but it was important for regularization, especially for that out-of-domain generalization. It helps keep the policy from wandering too far away from the capabilities of the base model.
Okay, and they did test bigger models too, right, in the appendix?
They did. Preliminary results on 7B, 14B QN models, and even Llama. The appendix notes show promise, but also highlight that scaling up likely requires more careful tuning of prompts and hyperparameters. It wasn't just plug and play at larger scales yet.
Okay, so let's try and pull this all together. What are the big takeaways here? What does INTUITOR and this RLIF idea mean for people actually building or working with AI systems?
Well, I think the big one is that it demonstrates a viable path towards training really capable reasoning models without needing that huge, expensive effort of collecting perfectly labeled data or building custom verifiers for every single task.
Which could be huge for tackling new or more niche problems.
Definitely, and it points towards greater potential for scalability and more autonomous learning. If models can learn effectively from internal signals, that could be key for AI systems that need to operate in complex environments or on tasks where human feedback is just slow, costly, or maybe impossible to get.
And the paper mentioned some future directions.
Yeah, the obvious ones are scaling INTUITOR further, seeing how it performs on truly massive models. Also trying out this self-certainty reward idea with other RL algorithms, not just GRPO things like reinforce or PPO, and maybe exploring ways to combine self-certainty with other signals, perhaps some sparse external rewards, or even just rewards for formatting the output correctly.
Makes sense. So wrapping up the core findings then.
Yeah.
INTUITOR, using just the model's own self-certainty, matched supervised performance on math,
while showing significantly better generalization to other domains like code.
and fostering these really interesting emergent behaviors like generating structured reasoning steps before the answer.
Yeah, it really feels like a significant step forward for this RLIF idea, this notion of leveraging what the model kind of already knows or feels about the quality of its own outputs.
Hopefully this deep dive gave you listening some solid aha moments about the potential locked inside these models' own internal signals.
And it leaves us with a pretty interesting thought, doesn't it? If models can learn complex reasoning just by optimizing how confident they feel, what happens when those internal self-certainty signals become really, really sophisticated?
Could that lead to AI systems that can genuinely explore and master completely new fields, skills we haven't even properly defined yet, guided mostly by their own internal sense of what feels right or correct? Something to definitely chew on.